I'd like to look at a specific projectile problem with the idea that we can use it both to understand some of the concepts involved with projectiles and some of the problem-solving strategies that will help you solve these problems. Here's the specific projectile problem I'd like to start with. It says, a rock is thrown horizontally with a speed of 5 meters per second from a 50-meter high cliff. Ignore air resistance. How much time will it take to land? How far from the base of the cliff will it land? And with what speed will it land? So of course, you know me, when I have a problem, the first thing I'm going to do is draw a picture of it. Not necessarily a fancy picture, but a picture. Let's let this be the cliff, and here's the base of the cliff. We have this rock. So there's the rock. It's being thrown horizontally to begin with, so just sideways whoosh lines. And in terms of projectiles, what we know about projectiles is that gravity is the only force, and it pulls straight down. So there's only a vertical force, meaning the acceleration is just in the y direction. There's no horizontal acceleration. So again, think of the motion sideways and the motion vertically independently. The motion sideways is a constant velocity. There's no acceleration. The motion vertically is a constant acceleration. The velocity is constantly changing because gravity is the only force acting on it. So let's draw in the ball from an x and y perspective. So what we can think about is, if this thing's moving sideways, then sideways, it doesn't speed up or slow down. So if I just think about it sideways motion, the sideways motion is a constant speed. It covers the same distance every second. So I could represent it sideways motion. From a vertical perspective, it's not moving vertically to begin with at all. Its initial vertical velocity is 0, and it's being pulled down by the force of gravity. So it's going to constantly accelerate at a rate of 9.8 meters per second, meaning in the first second, vertically, it might only go a small distance. And in the next second, it might go even further, and so on. We're expecting it to change its velocity constantly in the y direction. So putting this together for the path of the projectile, we can see that it covers the same distance horizontally each second, but that it speeds up vertically. So that's the path of the projectile. And what we're looking for in this problem is, well, how much time does it take to land? How far away from the base of the cliff does it land? And what is its final speed? When it's hitting the ground, how fast does it move at that last moment? So let's look at the first one. How much time does it take to land? Well, because these motions are independent, it takes the same amount of time to go sideways and drop as if it was just drop from rest to begin with. Meaning because this is thrown with just a horizontal speed to begin with, the time it takes to hit the ground is the same as if I just held it at the top of this cliff and dropped it. So we're going to look at that. I could just start the problem and say I have a 50-meter high cliff and I'm dropping something. How much time does it take to land? But let's put the whole problem together, and we're going to make an x and y chart, or a horizontal and vertical chart, just to look at our information. So horizontally, I'll call that x. Vertically, I'll call that y. I'm going to lay out my information here, and just because I'm going to run out of room, I'm going to solve my problem over here. So in the x direction, I might know things like the change in position, the initial velocity, the final velocity, the acceleration, and the time. And those are the same things I might know from a y perspective. So those are often the variables I might have. Let's see, in this problem I know the initial speed, which is a horizontal or an x piece of information, so put that in for VIX. I know it's only thrown horizontally to begin with. So that means there is no initial y velocity. It's not thrown down, it's not thrown up, it's just thrown sideways. So there's no vertical y velocity. I'm going to put 0 right here. I also know that it's going down a distance of 50 meters. So this distance here is 50 meters, that's vertical information. It means that the change in position vertically is going to be down 50 meters, or negative 50 meters. So I'm going to put negative 50 right here. And the last thing I know is that it doesn't accelerate horizontally, there's no force horizontally. So this x acceleration is 0. And it does accelerate because of gravity vertically. So vertically the acceleration is negative 9.8 meters per second. So there's my information. I like to solve right underneath here, but you won't be able to see it. I like to solve right underneath here, but you won't be able to see it. So we're just going to move over a bit and show how to plug these numbers in. For how much time will it take to land, really however much time it takes to go sideways is the same as however much time it takes to go down. So you can use y or x information to solve for time. That's the only thing that will be guaranteed to be the same on both sides. So using the y values, I'll use this equation. Delta d is vi t plus 1/2 a t squared. And I'm just going to stick to the y side. So negative 50 equals vi times t, well, that's 0, plus 1/2 times negative 9.8 times t squared. And then when I solve it all for t, I get 3.2 seconds. So it takes 3.2 seconds if you just dropped it, or if you throw it sideways at any speed and let it fall. The time is 3.2. I'll write that here. That's my answer to A. And that's also the time it takes to go sideways. For B, I'm looking for a y piece of information. I want to know how far sideways does it end up. So I'm looking for some x distances. So for B, I'm looking for this thing in the x column. So I'm going to try and squish this equation on the x side. I just want to work on the x side. Delta d equals vi t plus 1/2 a t squared. What a squish. And to solve for the distance x, I'm just going to use the numbers on the x side. And now I have another number on the x side. I've got this time. So delta d equals VIT, 5 times 3.2, plus 1/2 times 0 times t squared. Oh good, that's going to go away. So the change in position sideways is just 5 times 3.2, meaning sideways it goes 5 meters every second for a time of 3.2 seconds. So the total distance sideways that it goes is 16 meters. Meaning it's going to end up 16 meters from the base of the cliff. Now for C, I don't really want to solve for C mathematically. I'd just like to talk through the process in case you're given one where you're asked to find the speed that it'll land at. Meaning you want to know right here what those final whoosh lines are like, how fast it's going at the end. I just want to talk through methodology. Methodology-wise, you'd solve for the final y velocity using this side. You'd solve for the final x velocity using this side, and then you need to put them together. Meaning the final x velocity is vx, the final y velocity is vy, and what you'd be looking for if you're looking for the overall speed, you'd be looking for the magnitude of this resultant. That's the v total. So you use a little Pythagorean theorem with numbers from here. So hopefully this gave you some overview of how to solve projectile problems and also some of the concepts involved in projectile problems.